let's talk a little bit about atomic structure. All right, in this video, we're going to talk about the structure of the atom. We're going to look at the subatomic particles that make up the atom, and most importantly, we're going to look at how we can use atomic symbols to describe the composition of an atom. Okay, so this is an atom. You've seen drawings like this. This is actually a pretty good model for most of our purposes. This part here, of course, is the nucleus. The nucleus is in the center. And the nucleus contains the protons and the neutrons. And a term that I don't see very often, but I think it's a useful term to use, that these two things together, the protons and the neutrons, because they're in the nucleus, these two things are sometimes called the nucleons. So nucleon is a term that means the nuclear particles, and both protons and neutrons would be examples of nucleons. And then, of course, outside the nucleus are the electrons, right? So this this model, this kind of drawing is fine for us. I do want to mention quickly that this model is not really very accurate in its scale or in its appearance. There are a couple of things. If you're actually looking at a real atom, there are some ways in which this model is not really very accurate. One is the size. This is kind of hard to see in this drawing, but this is an example of an atom, just kind of roughly defined by that sphere, right? And that's actually one of the things that is unusual about atoms. They don't really have a hard shell on the outside. They're kind of diffused, more like a cloud than a beach ball or a bowling ball or something. So they don't really have a well-defined radius necessarily. There are ways that we can define radius for atoms, but they're kind of soft and squishy on the outside. And the electrons, rather than going in orbits as depicted here, really exist in this space around the nucleus as something closer to kind of a cloud. In fact, we often call this an electron cloud to define that space there. And then the other thing is the image over here on the left. Of course, the scale is not really very accurate, and that's okay, but I just wanted to point out that in reality, the nucleus is down here, and it's extremely tiny relative to the size of the atom. All right. A lot of books have some kind of an analogy in them, and they'll say something like, if the atom was the size of the Rose Bowl, the nucleus would be like a baseball sitting on the 50-yard line or something like that, or maybe a golf ball or a BB or whatever. Doesn't really matter what the exact size ratio is, but just that the nucleus is really, really, really tiny, and most of the atom is made up of just empty space. Okay, so let's look a little more closely at each of these subatomic particles. First one is the proton, and we don't use these symbols very often, but we will in this particular chapter while we're focusing on subatomic particles. The symbol for the proton is P with a superscript plus. The charge on the proton is 1.6 times 10 to the negative 19 coulombs. Coulomb is an SI unit of charge. And in an atomic species, everything comes in units of 1.6 times 10 to the negative 19 coulombs. So something could have a charge of 1.6 times 10 to the negative 19 coulombs, or if you had 2 protons, it would be 3.2 times 10 to the negative 19 coulombs. If you had 3, it'd be 4.8 times 10 to the negative 19 coulombs. So it's useful to just think of this as 1 unit. And so instead, or let's say 1 unit of charge. So instead of using this number all the time, we usually would just say that the charge is +1. And we understand that to mean +1 means +1 of those. All right. Sometimes this charge here is sometimes given the symbol E. And so you could sometimes see this charge is written +1e. We won't do that here, but you might see that in some cases. Okay. All right, and the mass of the proton is 1.0073 AMU. You don't have to know this number exactly, but you should know that the mass of a proton is very, very close to 1 AMU. Right? AMU is atomic mass unit. So the mass of a proton is essentially 1 AMU, and the charge is +1. All right, and the next particle is the neutron. The symbol for the neutron is an N with a superscript 0. These superscripts, of course, represent the charges, right? So the charge on a neutron is 0 coulombs, and that means the relative charge is 0. The mass of the proton is almost exactly the same as the neutron, 1.0087 AMU. And again, you don't need to know that number, but you should know that the mass of a proton is almost exactly 1 AMU. Right? So if you have to do a calculation and you're trying to figure the mass of something, if you don't know the exact masses, you can just assume that protons and neutrons have a mass of 1 AMU, and that'll be correct to within, 0.1% of error. So that's a really good approximation. And the last particle, of course, is the electron, which has the symbol E with a superscript negative sign here. And the charge of the electron, of course, is the same as the charge of the proton, except for this one is negative instead of positive. And so the relative charge is -1. The mass of the electron is about 0.0005 AMU. Again, you don't need to know that number, but what you do need to know is that it is much, much smaller than the masses of the protons and the neutrons. If you do the math, you'll see it's about 1/2000th of an AMU. But when we're calculating masses of atoms and things like that, this is so small that a lot of times we just basically disregard it and just don't worry about the electrons and calculate the masses based just on the protons and neutrons, because they're so much larger than the electron, or their masses are so much larger than the electron. All right, so in talking about masses, we've been using AMU, which I just said is called an atomic mass unit. And the atomic mass unit is the unit of mass that we use for describing the masses of individual atoms or individual subatomic particles, right? If we're talking about some macroscopic object, like a vial containing water or salt or sugar or something like that, we would measure the mass in grams. But for individual atoms, they're so much smaller, it's easier to have a special unit just for those individual atoms. And so the unit that we're using is the AMU, or atomic mass unit. And the ratio of AMU to the gram is the same as the ratio of the atom to the mole, right? And that ratio is Avogadro's number, which has the symbol N. And this is a number that you'll need to know. So when we are measuring macroscopic quantities of substances, we talk about them in terms of moles, and 1 mole of a substance is 6.022 times 10 to the 23rd atoms of that substance, or 6.022 times 10 to the 23 molecules of that substance, depending on whether it's an atom or a molecule. And so the ratio of the number of atoms in a mole is the same as the ratio of AMUs to grams. So what that means is that 1 gram is equal to 6.022 times 10 to the 23 atomic mass units. Okay. And you should know this relationship. There are some calculations that you'll probably need to do using this number. And again, it's easy to remember just because that number right there is Avogadro's number, which is one that you should be familiar with. Okay, we can describe an atom and the subatomic particles in it by using atomic symbols. And when we use atomic symbols in this way, there are 3 special numbers that we'll put around the symbol, right? Where the E is the atomic symbol, for example, for iron, we would use Fe, or for nitrogen, we use N or whatever. So we can indicate what element we're talking about with the large letter, or in the case of 2 letters in the middle. And then we're going to use these 3 numbers here to help us to clarify how many protons, neutrons, and electrons are in that substance. So the first of these, down here in the lower left, is the atomic number. And Z is used pretty much universally for atomic number. The second one, left superscript here, A is the mass number. And this is a little bit less standard. Different books might use different symbols there. They don't always use A for that. But it's still going to be up here in the upper left. That's the mass number. And then Q over here, superscript on the right, gives you the charge of that atom or ion. Okay, let's see how all these things work. All right, so the first one, and perhaps the most important one, is the atomic number, Z, which is down there, the left subscript, right? And the atomic number tells you how many protons there are in the nucleus, right? So for example, if you had something like Fe26, that would tell you that this particular atom has 26 protons. All right, because that number is counting the number of protons, you can't have half of a proton or a tenth of a proton or whatever. So the number of protons here, this atomic number, is always going to be an integer. Okay. And when you look at the periodic table, there's no real standard way for people to put the numbers in the periodic table, right? So sometimes you'll see the atomic number at the top, sometimes you'll see it at the bottom. And the way you can identify the atomic number on the periodic table is that the atomic number is always the one that is an integer, right? There'll be another number on the periodic table that's not an integer, and that one is the atomic mass. Okay? So when you're looking at the periodic table, that is the atomic number, and that tells you how many protons you've got. All right, and then the really, really most important thing about the atomic number is that the identity of the atom is determined by the number of protons. Okay, so for example, in this one we had down over here, right, iron with an atomic number of 26. This means that there are 26 protons in the nucleus, right? You'll see in a minute that we can have atoms with different numbers of neutrons and different numbers of electrons, but for any atom of iron, it's always going to have 26 protons. And the fact that it's an iron atom is actually defined by this 26. If it had any number of protons other than 26, then it wouldn't be iron anymore, right? If it had 25 protons, then by definition it would be manganese. And if it had 27 then it would be cobalt. Right? So if you look at the periodic table and you see the atomic number here, you know that every neon atom has 10 protons, and every atom with 10 protons is neon. All right, the next one is the mass number, and the mass number is the sum of the protons and the neutrons in the nucleus. In other words, it's the number of all of the nucleons, right? And because the masses of the protons and the neutrons are both really, really close to one atomic mass unit, the mass of the atom is going to be very, very close to the mass number, right? The difference is that the actual mass of the atom may not be an integer, right? Whereas the mass number is going to be an integer. The mass number, because it's a counting number, it's the number of protons plus the number of neutrons, so it's got to be a whole number like 5 or 12 or 72 or something like that. The actual mass of the atom may end up being something like, instead of 72, it may end up being like 72.0015 or something like that. But the mass number will always be an integer. And you'll see that, as we said before, every atom of a particular element has the same number of protons. And we're using iron as an example before. All right. So iron has an atomic number of 26. So every iron atom has 26 protons. There are no exceptions to that, right? But we can have iron atoms with a mass of 56, right? Which would mean that there were 30 neutrons. Right? Or we could have, for example, an atom with a mass of 57, right? Which would mean that there were 26 protons and 31 neutrons, right? So the mass numbers can change, right? But as long as the atomic number is the same, it's going to be the same element. Right? And anytime you have an atom where you've got two different atoms of the same element with different mass numbers, those are called isotopes. Right? So these would be examples of two different isotopes of iron. Right? There's a couple of different ways that we can write these. The symbol, as I mentioned, the symbol that we're using right now is to put the mass number as a left superscript, and that's the way that we want to do that. But if you're looking at something in the newspaper or something like that, here's an example of uranium with a mass number of 238. People will sometimes write this like that, uranium 238, or sometimes 238. Okay. Again, this isn't a way that that we want to do that in this chapter, but I want you to be aware of that because this is the way you'll see this in sort of the public discourse in newspapers and magazine articles and things like that. That's a way of indicating the mass of different atoms. All right, and then the last one in the upper right up here is the charge. And in a neutral atom, the number of protons in the nucleus and the number of electrons outside the nucleus are going to be the same. And so if the protons all have a +1 charge and the electrons all have a -1 charge, that's going to cancel out, and the total charge is going to be 0. Okay. But atoms can gain or lose electrons, and if they gain or lose electrons so that the number of protons and neutrons are no longer equal, then the atom gets a charge. It can be a positive charge or a negative charge. And the charge is equal to the difference between the two of them. Again, if you got the same number of protons and electrons, then the charge is going to be 0 because the plus ones and minus ones cancel out. If there's a difference in those two, then you're going to end up with a net charge. Right? And because the protons have a positive charge and the electrons have a negative charge, it ends up the charge is the number of protons minus the number of electrons. Right? And so you can see from that, if you have more protons than electrons, you're going to get a positive number, and that means you've got a positive charge. If you've got more electrons than protons, then you're going to be subtracting a larger number from a smaller number, and so the net result is going to be negative. That means that species would have a negative charge. And an atom, which has either lost or gained some of its electrons to acquire a charge, is called an ion. Right? And among the ions, there are two types. If it loses electrons, it ends up with a positive charge, and we call that a cation. And if it gains electrons, it ends up with a negative charge, and we call that an anion. It looks like anion, but it's not anion, it's anion. Okay. All right, so let's take all of that stuff and put it together. This is what quiz or exam questions look like on this topic, typically. So we might ask for a symbol. Say, for example, what would be the symbol of a sodium ion with 12 neutrons and a charge of +1? Okay. So we can start with the atomic symbol. If it's sodium, we know that that's Na, right? The charge goes in the upper right, and we're told here it's got a charge of +1. So usually for the charge of its +1, we just write plus instead of writing +1. If the charge is +2 or +3, then I'll write 2 plus or 3 plus. I'm not sure why people have decided to write that as 2 plus and 3 plus instead of +2 and +3, but this is just the convention, right? So that's how we do it. If the charge is negative, you write negative or 2 minus or 3 minus. And if it doesn't have a charge at all, then instead of writing a 0, we just leave this spot here blank, right? This one does have a charge though, so we'll leave +1 there. All right, so we want to fill out the rest of this symbol. So if it's sodium, we can look at the periodic table and find the atomic number of sodium, and the atomic number is the integer with the sodium in the periodic table, and that integer is 11, right? And then we want to include the mass up here in the upper left, right? And this one has 12 neutrons, right? But the number that we want to put up there is not 12, because remember that the mass number is the sum of the protons and the neutrons. And so this atomic number means that it has 11 protons, and if we add the 12 neutrons to that, that means the total number of species in the nucleus is 23. So the mass number will be 23. All right, let's try another one. A neutral atom with 48 protons and 64 neutrons. All right, so in this one, we don't even know what element it is, at least not to begin with. But we do know that it's got 48 protons. So the number of protons is the same as the atomic number. We can look on the periodic table and find what species has an atomic number of 48. And if you look, you'll see that that is cadmium, which has the symbol Cd, right? So there's our atomic symbol. The atomic number is 48. We can put that down here. All right. And again, it's got 64 neutrons, so the mass number up here is going to be the sum of the protons and the neutrons. And if we add 48 and 64, I think we get 112. And since this is a neutral atom, that means it doesn't have a charge. Again, we could put a 0 there, and technically that wouldn't be wrong, but no one ever does that. The best thing to do is just to leave that blank. And if you leave that blank, that's interpreted as a charge of 0. Right. And so this atom would also have 48 electrons. We don't indicate the electrons because the number of electrons is implied by that charge, right, or lack of charge. All right, let's try one more. All right, let's write the symbol for an ion with an atomic number of 35, a mass number of 81, and a charge of -1. Okay. So again, we don't know what the element is, but we know the atomic number is 35. We can look on the periodic table and see that element number 35 is bromine. Right? And in this case, the mass number for the upper left is already calculated for us. So that's an 81. Okay. And the charge, Q, on the upper right is -1. So we can indicate that with just a negative. Right? So how many neutrons would this ion have? Right? We could ask that question. It's not in the question as listed here. Okay. Sorry about that. That was my phone. So we could ask the question, how many neutrons are in this ion, right? And if this mass number is the sum of the protons and the neutrons, that means number of protons plus number of neutrons equals the mass number, right? And that means that the, let's come down here, number of neutrons equals the mass number minus the number of protons, be 81 minus 35. And 81 minus 35 is going to be, let's see, 46, right? So this particular ion has 35 protons and 46 neutrons, right? And how many electrons does it have? That's another good question. So we know that the species has a net charge of -1, right? That means it has one more electron than it has protons. And since it has 35 protons, that means it must have 36 electrons. Right? Again, that wasn't in the original question, but that's the kind of thing you should also be able to answer. Right? All right, there are a bunch of problems like this in the study guide, so work through these and make sure that you can take descriptions of atoms and use those to construct atomic symbols. And although we didn't do it here, you should also be able to take an atomic symbol and go back to a description. So if you have this symbol here, right, you should be able to say this is a sodium atom that has 11 protons, 12 neutrons, and 10 electrons, right? Because it's got one more proton than electron. Okay. All right, so work through those in the study guide. Make sure you've got this down. Okay, so what we talked about were the parts of the atom, the protons, neutrons, and electrons. We talked about the properties of those, the masses and the charges. What's most important are the relative masses and charges. So the protons are +1, electrons are -1, the neutrons are 0, and then for the mass, the protons and neutrons both have a mass that's really, really close to 1 AMU, and the electrons have a mass that's much, much smaller, and in most cases, essentially negligible. We pretty much can ignore the mass of the electrons and worrying about and trying to determine the mass of an atom. All right, and Then we looked at these atomic symbols, right, where we use the atomic symbol in the middle, and we can put the atomic number in the lower left, the mass number in the upper left, and the charge in the upper right. And based on this symbol, you should be able to determine the number of protons, neutrons, and electrons in that atom or ion. All right, terrific. Practice those problems, have a lot of fun, and then we'll be back with another one